Yeah.
All right. Okay. Without further ado, let's thank Graham for taking the time and giving this talk. Graham is a professor at Warwick University. He's also a faculty fellow at the Turing Institute, and I think the lead actually for Warwick at the Turing. He's done a lot of work on sort of the algorithmic aspects and theoretical aspects of privacy in general and differential privacy. And today is going to talk about local differential privacy in federated analytics. Thanks, Graham.
Great. Thank you for this invitation. Yeah. So I was reviewing the slides for my talk earlier today, and I realized that in my slides I never actually really explain what I mean by federated analytics. So I should probably start by introducing this notion. So if you managed to catch Vitali's talk, the previous talk in this series, he gave a great overview of federated learning and some work he's been doing there. And so you can view federated analytics as being very much in the same realm as federated learning, right? So in a nutshell, federated learning is when you're trying to learn, do some machine learning over distributed data, and in particular where you want each user has their own data set or set of small examples, and you want to make sure that those examples stay on the user's device, and you just capture some information pertinent to the current state of the model to improve that model, do the training. And federated analytics is really saying take exactly that same model of computation with the same motivations and goals. So the same idea that restricting who gets to see the data, keeping it on the client device, is hopefully giving you a stronger guarantee of privacy. But broaden the outlook to say, well, it's not just training machine learning models we want to be able to address, but it's all kinds of questions to do with understanding and analyzing data. So in some sense, you can almost think of this notion of federated analytics as an attempt to be broader even than federated learning. And again, just as with federated learning, you can have different notions of exactly how much privacy you'll enforce. And so what this talk is trying to do is sort of sketch out how we can bring this particular notion of local differential privacy together to solve various analytics problems. Right. So in very brief overview, I say it's a recap of local differential privacy, maybe it's an introduction, and some of the problems in frequency. And depending on how things go, I may end up spending most of my time talking about sort of these fundamentals of how do you essentially capture frequency distributions in this particular model. And then I'll go on to talk about some of my joint work with Tejas Kulkarni and Devesh Srivastava on capturing marginal distributions and range queries, and maybe just a very brief snapshot at the end of some of the questions that I'm thinking about at the moment. Okay, so let's sort of introduce our notion of privacy and our privacy primitive. I want to go back all the way to the last century, in the middle of the last century, and this very sort of simple concept I'm sure many of you seen before of randomized response. So our scenario is we're going to do, we may even claim that this is federated analytics, but we're actually going to do a very simple data gathering exercise. So let's assume that everyone in our population, each one of you listening to this talk, has a single private bit of information. Right, so it's a 1 or a 0, a yes or a no, and that's encoding, your political preference, whether it's left wing or right wing, maybe something about other protected characteristics. And obviously, many of these examples you would probably object are not really binary in any sense, but let's solve the binary problem first, and it should be fairly easy once we solve the binary problem to generalize it to higher cardinality questions. Okay. So the reason I particularly like this is I think that this is probably the simplest formal algorithm that gives any kind of privacy. And indeed, it's probably the simplest randomized algorithm, because the entire algorithm is on these 3 lines, at least as far as each user goes. So take your bit, your yes or your no, take a biased coin, throw that bias coin so that with probability P, it comes up heads and you report your true answer. So you report your yes, say, or otherwise with probability 1 minus P, you will lie. You'll say no, even if your answer was a yes. And so that in itself gives you plausible deniability. And so the sort of the back end of this algorithm is that every user in our population will tell us a yes or a no, and we don't know whether that's a true yes or a lie. And so on an individual basis, we don't really know what's going on, but collectively over a large population, we are able to estimate the sort of the proportion of the population. So do most people in the population say yes to this question and most say no? Is it about 50-50? Essentially, you can use your knowledge of this procedure, use your knowledge of this probability parameter P, write down an equation, rearrange it, and get an expected value for that population fraction based on the observed number of responses. And you can also fairly easily work out the variance of this estimator. And you'll see then that the error, your uncertainty, will tend to go down proportional to 1 over square root n, square root the number of people that you asked. And just to couch this in terms, I'm doing my very best in this talk to not give the formal definition of differential privacy, because I think enough people have seen it enough times. But just to say that you can map this concept from from many decades before differential privacy was even suggested as a concept. You can map it onto differential privacy. It's simple enough that you can just express the differential privacy parameter epsilon as based on this function of the parameter P. So great, this is a slide. I've told you an algorithm, I've told you its analysis. Whenever I talk about this and I start talking about tossing coins and saying yes or no, it often feels like the kind of thing you'd have on a probability exam, right? It seems so sort of simple and trivial almost that it's just sort of an exercise. And so what's intriguing about this is it has sort of become the grounding of this notion of local differential privacy, right? This coin tossing randomized response procedure is essentially the kernel of just about every locally differentially private algorithm, with some embellishments and a lot of structure built on top. And more than that, right? It's maybe the leading example of where this notion of differential privacy has been developed, deployed, and used on a very wide scale. So at least for a while, Google's Chrome browser was using ideas built on this to capture information about people's browsing habits. Microsoft and Apple have both implemented and used versions of protocols built on these kind of coin tossing techniques to collect information about how people are using different apps. Maybe close to the federated learning world, the Snap company who run the Snapchat app have also built various sort of spam detection models based on this kind of local differentially private data collection. So this has meant that these kind of algorithms, these kind of ideas have impacted and affected, maybe not consciously, but subconsciously, hundreds of millions of users. And that's quite a big deal, because when we think about these kind of statistical privacy techniques, up until maybe 5 or 6 years ago, we had a lot of technical understanding of them. We didn't have that many examples of where they'd really been used, at scale in the wild. So this is sort of the vanguard of that, these techniques coming into practical use. This is something for any British academics at the moment who are sort of dotting the I's and crossing the T's on ref submissions, should be thinking about their impact case studies. Well, this is a great example of something where sort of the core technical work was done maybe 50 years, 5+ decades before the actual impact was seen. But when it was seen, it was really quite substantial. Okay, so let me sort of fill in a bit more details on how some of those deployments actually worked. Right, how do you go from this sort of toy coin tossing example into being able to collect statistics over data over a large domain over a large population. So the main thing we need to do is to think about, well, how do we go from just binary yes/no information into when people may have one value from a large collection, right? So think of examples where Google was trying to collect information about people's browsing habits, and they wanted to know were there URLs that were suddenly becoming particularly popular. So the abstraction that's been developed is this idea of a frequency oracle, right? It's saying, can we build up extensions of the randomized response algorithm that allow this aggregator who receives all these reports to be able to estimate the frequencies of items from a large discrete domain. Okay, so when your discrete domain is just binary, then randomized response is pretty much the only thing you can do. You could try and define other solutions, and they all end up being isomorphic to randomized response as we've described it. And when your domain is very small, so not 2 options, but maybe 3 or 4 options, you can easily come up with a generalization of randomized response, where instead of picking the unique alternative with a certain probability, you pick each of the 3 or 4 possible alternatives with uniform probability. And you can then start to sort of write down the equations, if you want to guarantee differential privacy, which tell you how to set your probabilities to ensure that the truth-telling probability is not too much larger than the lie-telling probability. And what you find is that this works okay for small domains, but as the domain gets larger, essentially this constraint on the ratio of probabilities forces the distribution of possible outputs for each user to look more and more uniform. And the more uniform each user's output is, the less information it's conveying, even in aggregate. So what you can do is, when you're dealing with very large or increasingly large domains, you can use a few more tricks, and these are mostly sort of algorithmic tricks involving sort of hashing or related notions, where essentially you hash your item from a large domain down to a smaller domain, report information about that hash value. And again, on the individual report basis, this doesn't tell you very much, but when you get enough reports from a large population with a particular distribution of values, that is enough information to reconstruct that distribution. And several of these techniques use the notion of the Hadamard transform, which seems to crop up a lot in this area. And don't worry if that's not familiar to you right now, because later on in the talk I'll go into a bit more detail about what that is and what it's doing here. But when your domain gets super large, you need even more sort of heavy technology, and the standard idea is to sort of use additional notions of dimensionality reduction, or sometimes called sketching, to the input. So you first get every user to encode their data using one of these sort of dimensionality reducing techniques called a sketch. And then essentially what you're doing is you're applying this frequency oracle that you've built, these notions of frequency oracles defined on this slide, to then capture information about the sketch, which in turn, once you can then query the reconstructed sketch to tell you something about the input distribution. Okay, so this is my chance for a bit of free advertising. So if you're interested in finding out more about sketches and other kinds of data summaries, then please check out the book that I published with Kevin Yee last year on exactly this topic. And you can go to this website and just download that freely and take a look. But the basic idea here, sort of the neat part of this idea of how this fits in with this sort of local differential privacy analytics, is that these sketches are typically sparsity preserving. So that is, you can think of each user's input as being a one-hot vector encoding over a very high dimensional space, and the sketch encoding of that input gives you an almost equally sparse, maybe it's not one hot, but the number of non-zeros in the sketch encoding is maybe still single-digit numbers. so that you can then take that sparse encoding of the input and run it through a frequency oracle which is expecting a sparse input, and everything just sort of works out. So there's lots of technical details here to sort of work through, particularly if you want to analyze this using sort of the tools of concentration of measure and variance calculations, but it all more or less goes through. And so you can sort of interpose these notions of sketching within these frequency oracles, and everything works out. So what that gives you is that gives you a way to build this sort of data structure that's held by the aggregator, built from all of these individual reports from a large user population. And what that data structure gives you is it gives you, the frequency oracle, so it gives you sort of oracle access to the frequency distribution. You can say how frequent was item XYZ, how frequent was item ABC. Another part of this puzzle is to say, but how do you find what you're looking for, right? So when your domain is very large, again, think of the space of all possible URLs. It's not that you want to query particular URLs so much as you want to discover which are the URLs that are frequent. But this maps onto this problem that's known in the non-private setting as heavy hitters. And again, many of the techniques that have been developed from the sketching and streaming community transfer across here to the federated analytics setting. So you can look at some of the ways that people have done this in the literature. There's some sort of statistical approaches that there was a paper from Google building on their rapport work that was using this sort of looking for statistical correlations to kind of reconstruct strings from fragments of strings encoded through frequency oracles. Or Apple's approach described what they called a puzzle piece algorithm, where again you would sort of glue fragments together. But what I think is the most natural and maybe the most intuitive, at least to me, approach is this sort of hierarchical prefix extending approach. So the idea is hopefully relatively simple. You can think of overlaying a hierarchical structure over your domain of all possible possibilities of all possible strings, so that every node in this hierarchy is going to correspond to a prefix of a particular string, or rather it's the prefix of all strings that extend that prefix. And you can build, instead of just building one frequency oracle on the whole input distribution, you can also build oracles on all prefixes of your input strings. And then it becomes almost a sort of depth first search. You look for, in this example, you'll sort of start and look for all strings, let's say all strings of length 2 characters, and see which ones of those come up as frequent, as heavy items based on your frequency oracle for prefix of length 2. And then you can ignore all the prefixes of length 2 that don't appear to be frequent, and start to query, well, what about all possible extensions of the ones that are frequent, and descend this hierarchical structure. And at the end, you'll hopefully find just those items which are heavy hitters and therefore interesting to you. So this is something that's of interest to me, and so I spent some time last summer working with an undergraduate research student at Warwick, where we said, well, let's kind of put all this together and try out essentially lots of different variations, try and sort of flesh out this framework of possibilities and see what we can find, right? Because if you think of it, you can decompose a method for finding these interesting frequent items within a domain by essentially sort of picking off a menu. You can say, okay, well, what kind of frequency oracle will I use? What kind of sketching dimensionality reduction will I use? You have a variety of options, or you can just essentially have the identity function. Which of those different heavy hitter searching strategies will I use? And additionally, you can do a little bit of post-processing. Right? Sometimes there are some additional optimizations you can do on the statistics that you gather from the population that will slightly improve the results that you get. And so if you look at sort of any of those large deployments we talked about earlier, like the work from Google, from Apple, from Microsoft, you can essentially express it as a particular tuple of choices from this menu. And indeed, there also by implication, there are a whole bunch of other choices you can try by making different selections. So we're sort of in the final stages of writing this up for submission. And I think what we found is maybe not radically surprising, but maybe useful empirical study. The main sort of highlights, I think, were that we talk about the usefulness of dimensionality reduction, but it turned out that it was only really a useful technique when the domains were really very large, more than maybe tens of thousands of items in the domain. As anytime you're dealing with a sort of a domain with fewer than that, then some of the other hashing based techniques work pretty well. And those hashing based oracles definitely give you the best accuracy, but they can be painfully slow because there's a lot of work to do for that decoding. And lastly, just to say that sort of the original paper that kind of, I think, launched a lot of the practical interest in this work, which was the rapport paper from Google, that advocated using an approach based on Bloom filters. But the work that came subsequently, I think, has shown that other approaches tend to dominate that. This sort of picture here, this heat map, is just to show empirically some of those results. So this is some sort of human activity data from a US city. And so you can see it sort of overlaid, the heat map is overlaid on a map. It doesn't take too much sort of geographical knowledge to realize that what you're seeing here is Manhattan, with the East River and the Hudson River on either side. And this sort of rectangle carved out the middle corresponds to Central Park, right? This was vehicle activity, and you don't get that many vehicles in Central Park, but you do get a few. There are a couple of roads that cut through, so there's sort of a few sort of light blobs of, I think, mostly taxi activity running through Central Park there. So let me move on to some other work that I've been involved with over the last couple of years. And this is where we wanted to look at going beyond this sort of one-dimensional view of data and saying, what about sort of multi-dimensional views of data? Well, what does that mean here? So here the notion is, instead of having just one attribute that defines you, you may have essentially a feature vector encoding, again, data about you that may be considered sensitive. And again, at an individual level, maybe we're not particularly interested in what any one individual has, and indeed for privacy reasons, we probably don't want to know any one person's feature vector. But we are interested in understanding the distribution of combinations of features over population. Right, so again, here's sort of a cartoon example. So we'll keep it simple again by assuming that we have just binary features for each individual. And if this is our sort of raw population, our raw user data, we want to come up with protocols where each user will report some information about themselves that's private, that gives them this plausible deniability, but would let us construct these kind of marginal tables that said across a particular combination of attributes, this is the probability distribution. And in some cases, you would see that essentially there's no particular correlation between those two attributes, and in some cases you would see that there was an interesting correlation. So given sort of this framework, given the kind of technical building blocks that we have, what are the kind of things that we could do here? We know we're going to make use of randomized response in some form or other. And the reason that this isn't just sort of a straight out repetition of the kind of frequency oracle work we've done already is that each user is now effectively contributing to a larger number of potential marginals. And so if we collect more information about each user, we want to still give a strict differential privacy guarantee, we have to start adjusting this probability of truth-telling P. And essentially, the rules of the game basically boil down to the more information, the more bits that a user reveals that have some private information in them, essentially the closer P gets to being half. And at least in this binary case, P equals half is just tossing a coin and reporting the result without looking at the data, right? P equals half is just random noise. So we need to sort of think about what's the design space of algorithms that will minimize the private information that we extract for each user, but somehow maximize globally the knowledge that we get about the population. Within this area that you sort of learn a few tricks. So one of the tricks that you learn quite quickly is essentially that if you ask n different questions to a user, then broadly speaking, the error in the information you reconstruct goes up linearly with n. But if instead, if I've still got my list of n questions, but I just get each user to answer one question, so I effectively divide my population into little n groups, the error only scales proportionately to square root of that little n. So somehow asking a single question to a smaller number of people is actually better than asking multiple questions to a large group of people. Okay, so what are the kind of things we might come up with? Kind of approaches we thought about were sort of the obvious sort of direct materialization kind of things. You might reveal information about all marginals that you're interested in. You can just count how many different marginals there might be. So of all marginals of size k out of d different attributes, there are d choose k marginals, and you could sort of try and materialize each of these separately. You could try and materialize the full joint distribution. So this is a much larger object, but you can still apply sort of randomized response to this and aggregate that, and then sort of project down into subspaces for whichever particular marginal of interest you want to find out. Or indeed, we didn't look too much into it, but you can think of other strategies that try and sort of do things in between. So what we found is you can analyze both these, and after a fair amount of arithmetic and calculation, you can write down expressions for sort of the expected error. I think of this as sort of expected absolute error in reporting these marginals, in reporting any particular marginal. And you can kind of squint at these for a bit, or try substituting some numbers in and convince yourself that maybe one method is preferable to another. But this is where I wanted to come back to Hadamard. This was sort of a different tack for this problem. So I mentioned Hadamard transform before. What is it? You can think of it in a number of different ways. It's this very nicely structured -1 + 1 entried matrix. You can think of it as essentially a kind of Fourier transform. You can just think of it as some random looking orthogonal matrix. But it has a lot of nice features. So one of the features, which is, I think, fairly well known from the functional analysis community, is that for exactly this problem of constructing the marginals, naively you would think, this is a transform that you could apply to some data, that naively you might think, okay, well, I could transform the data using this transformation, capture information about all the coefficients of the transform, and then reconstruct and invert the transformation. But if all you're interested in are the marginals, you don't need all the coefficients, you need a smaller subset of them. This d choose k coefficients is sufficient to reconstruct any of these k-way marginals. So that's good. That reduces the amount of information we're trying to capture. The other property, which again is sort of obvious if you look at this expression of it, it's a matrix. So it's a linear transformation. And what that means is basically, if I want to find the Hadamard transformation of a collection of data, right, of all the data of all my users, I can just take the Hadamard transformation of each user's input separately, add up those transformed values, and the summation of the transforms is the transform of the summations. Right, so that means it will sit very neatly within a framework that allows you to do this sort of sampling and averaging operations on data. And so when you work this one through, you get this kind of error guarantee, which is stronger than both the previous methods. Well, stronger in theory, and we all know from any kind of sort of experimental algorithms work that you still then need to try it out in practice and see what you actually get. So this is the kind of thing that you see when you try it out in practice. So just to interpret these plots, you know, the y-axis is showing this measure of error, this is total variation distance, or this sort of sum of absolute differences. And we're showing 3 different approaches that we could have tried. And the main thing to take away is the proposed approach that we have here is achieving that's based on Hadamard transform and randomized response on those Hadamard observations, is achieving the smallest error, so hence the most accurate reconstruction, as we look at, you know, about 500,000 individuals and low degree marginals over sort of tens of possible dimensions. Okay. And sort of with this work, you know, you can then say, well, what does this get you? Well, once you have marginals, you can do a bunch of things. So you can look at different kinds of, let's say, graphical modeling problems, right? So what's the simplest graphical model you might want to build of your data? Maybe a Bayesian model. So what we're trying to do here was to say, okay, if we gather the information through this kind of locally private mechanism, and then try and build a graphical model based on this, how good is the graphical model compared to what you would get without privacy? So this sort of tall pink bar is capturing the accuracy of a measure of quality of the model based on mutual information if you didn't have any privacy concerns, if you just worked directly with the raw data. And the green and the red bars are saying, you know, this is what you get using the approach based on Hadamard transform, and the red bar is the approach based on just trying to capture information about a bunch of marginals. And you know, a few more things you can do. We looked at sort of significance testing, and again, this is what this plot is showing is you want to run a bunch of significance tests on in this case it was a correlation query, and you know, the thick black line is your significant value, your critical value of the test statistic. So what you wanted here really was just that your approximated value from the noisy data collection was on the same side of that line as the true value. And in most cases it is, and in some cases it gets a little bit close. But still, you know, in many cases you can kind of end up with the same answer. Okay. In the interest of time, I'll probably skip this section, but just to say, you know, we also looked in a follow-up paper about 1.5 years ago, going back to the one-dimensional case, but saying instead of wanting to estimate individual frequencies, can you answer queries based on a range of values, right? So I want to find how many people have a value between 1 million and 2 million in my data set, for whatever that might encode. And similar kind of collection of techniques turned out to be useful there, ideas based on making use of frequency oracles, but thinking about different ways to transform and encode the data before putting it into those frequency oracles. So again, don't try and look at the details, but sort of techniques based on hierarchical representations, some sort of normalization and enforcing constraints, some techniques based on transforming the input based on an appropriate orthogonal transformation turned out to be useful here. I'll save those, and if people are interested in the slides, I can make them available. So I'm going to start wrapping up now. That was sort of a pretty quick high-level overview of this idea, this question about how can you gather information from a large user population and learn statistics, learn parameters about that population while enforcing this particular model of privacy. So some of the things I've been thinking about more recently are sort of trying to go off in other privacy directions. So hopefully one thing we may hear about more in this series is sort of other models. So one of the main limitations of the local differential privacy model that we find is, yes, you can deploy it if you're Google, Microsoft, Apple, because you have millions, if not tens of millions of users that you can opt in to your data collection procedure. But certainly, if you look at the way that the accuracy of the answers that you get goes, you need those millions of users, right? If you only have thousands of people participating in a protocol, then the noise for privacy just outweighs any signal that you can extract. So there's a lot of interest across the privacy research community in saying, well, how do you get a better trade-off between privacy and accuracy? So a lot of work going on in people trying to use sort of multi-party computation techniques to gather the data and aggregate it so that no or less volumes of noise are needed. Something that sort of emerged in the last 3 or 4 years is this notion of a shuffle model that looks a lot like the local privacy federated analytics model, but says, well, what happens if we can sort of formally dissociate the identity of the user reporting a message from the contents of that message, right? So the way that you might be able to implement that are if you have some sort of intermediate trusted third party that essentially performs this shuffling, that takes away the information that links the sender of a message to the information in that message. So there's a bunch of results, particularly from people associated with the Turing Institute. Adria, James Bell, Borja Bal have been working on a lot of this, and this is sort of something I've been working on with Carsten Maple and Mary Scott, my PhD student, trying to understand, what else can we show in this model? What other kind of techniques can we apply? Working with Nina Stausholm from Denmark, I've been looking at adapting different kinds of sketching techniques and combining them with privacy. So as well as the kind of sketches we saw that capture raw frequency information, there's a lot of sketches that capture cardinality information about the number of distinct entities that are participating. So this has a lot of applications, let's say in sort of the online advertising domain, where you want to capture information about, for a particular advert, how many people are actually exposed to that, given that the places where they may see that advert are many and varied, and you want to not have to capture detailed tracking information about people as they go about the web. So there may be ways to combine sketching and other kinds of variations of randomized response to capture information there. With Hakan Fahadsmanoglu and Terry Cunningham back at Warwick, there's another line of work to say, okay, well, you can build these kind of generic analytics tools for sort of questions like frequencies over a large domain, but what happens when you look at sort of more specific domains of data? So let's think about things like locations and movement patterns through the real world, and how can we take advantage of some sort of real world background knowledge, right? So if you're looking at cars moving around, then probably you expect those cars to be on roads, and you don't expect them to be in rivers, and incorporating that kind of information can help to improve the accuracy of noisy location reporting. And lastly, with Chris Hickey and Tom Gurr, I've been going sort of completely up into the skies, thinking about sort of new privacy models to do with zero knowledge proofs, where instead of looking at the computational limitations of your adversary, you can look at the space or the memory limitations of your adversary. So I think that's a good time to sort of wind things up. I'll end with a theme that I often end my talks with, which is to say that these questions about capturing private data, working with it, using these kind of techniques is a confounding problem. And there are, I kind of skipped it for this audience, but most times when I started talking about privacy to a general audience, you kind of go through this litany of all the times people with good intentions have got it wrong and released information which just has yielded, sometimes almost trivially, to simple attacks to re-identify people and actions within that. There is this maybe long-term aspiration that privacy protection could be as simple and straightforward as compressing a file or setting up an encrypted connection. For most people, they don't have to do any configuration or any thought for those kind of actions. But privacy compared to encryption is still far from configuration free. But again, we're seeing lots of causes for optimism. We're seeing lots of progress in this, that greater confidence from people in using ideas of statistical privacy, more deployments like the ones we talked about today are kind of moving that barrier forwards and at least on a technical side advancing the conversation about what's possible. And I think I don't probably need to tell this group, but there's so much opportunity for designing the approaches for different kinds of differentially private computations, particularly with all the excitement around machine learning and AI, trying to make every ML computation a private one. These new models, local differential privacy is relatively recent, shuffling more so, are helping us to sort of understand what's possible. And we have a reasonable grasp on certain kinds of structured data. So things that you can model as graphs and networks, things that you can model as trajectories, various kinds of activities. We are reasonably confident in. Equally, I think even just sort of formalizing what we mean about privacy when we start thinking about text or massive language models, images, video, multimedia, we're much further away from really understanding it. But that's always good for researchers because it means more opportunities for research. So with that, I will finish here, and yeah, we've got time for questions.
Fantastic. Thanks a lot, Graham. I'm going to stop the recording now. So just a second.